To understand the federal procurement market, we have to acknowledge a hard truth. Procurement decisions rely on data fragmented across thousands of disparate endpoints. The challenge is seeing the full picture when the evidence is scattered. The federal government spreads its purchasing footprint across 38 distinct sources. This includes award records, contract modifications, congressional bills, strategic plans, and hundreds of thousands of pages of regulatory text. Standard retrieval augmented generation and naive semantic search algorithms often fail in the procurement domain. These tools struggle to look past the repetitive legal boilerplate that saturates federal documents. We must build an architecture that isolates genuine procurement intent from the surrounding noise of standard legal formatting. Managing this data requires a multi-layered, hierarchical data science stack designed specifically for the federal ecosystem. This architecture is divided into 3 macro zones. The foundation aggregates and cleans raw inputs. The moat maps semantic taxonomy. The apex output delivers predictive intelligence. We will reconstruct the system layer by layer, beginning with source aggregation. Generating reliable predictive signals at the top of the pyramid requires a deterministic filtering process at the base. Before a single line of text hits an embedding model, it must pass through the foundation layer's cleaning pipeline. If you feed raw federal solicitations into a vector database, repetitive clauses and standardized IFG statements will dominate the embedding space. Without cleaning, a search for cybersecurity services might return unrelated contracts simply because they share the same legal headers. The solution is a deterministic cleaning pipeline. The system identifies and strips out 5,335 specific agency-level boilerplate phrases before processing continues. By removing the repetitive legal headers and standardized disclaimers, the resulting text represents the actual subject of the procurement, separated from its legal wrapper. Blinding the embedding model to the legal formatting forces the AI to evaluate the agency's true purchasing intent. With the text scrubbed of boilerplate, we move up the stack to the embedding layer, mapping the cleaned data mathematically. All text runs through the Qwen3 embedding 8B model, mapping each input into a precise 1024-dimensional space. The pipeline uses a dual embedding approach. Individual records receive instruction-prefixed retrieval embeddings, while long documents like strategy plans are chunked and receive structure-aware passage embeddings. The output of this stage operates at scale, generating 31 million record vectors and 19 million chunk vectors. This creates a single, unified vector space. A 2-paragraph contract modification can now be mathematically compared against a 100-page strategic plan on the exact same dimensional plane. The next hurdle is organizing that massive vector space into a coherent semantic taxonomy within the topic model stack. Text from a congressional oversight report clusters differently than text from a vendor award. We need a way to relate concepts across different types of documents. The architecture uses a 3-tier BER-topic hub-and-spoke model. The central hub is the topic backbone, trained on 20 corpora to dictate a canonical taxonomy. 27 domain-specific ground floor models radiate outward. Each spoke adapts to its register, mapping topics back to the central hub. This architecture ensures a common language across the graph. A query about what an agency says it needs in a strategic plan can be directly compared to what it actually buys in an award. We will step next into the knowledge graph layer, where these semantic models merge with structured relational data. The foundational ontology defines 19 object types, connected by 28 link types. The first layer is the entity graph, structured edges derived deterministically from federal data. Layered over that is the keyword graph, containing 3.2 million procurement-specific concepts extracted via keybert noun phrase mining. Aho-Karasik matching allows these keyword bridges to link polymorphically, connecting awards, long-form documents, and specific vendors across the database. This creates a dual-threat intelligence graph. Structured edges provide relational accuracy, while keyword bridges enable lateral discovery. A populated knowledge graph maps historical facts. To forecast future opportunities, we need a layer that anticipates new relationships. At the top of the moat sits a procurement-native neural network utilizing relational graph convolutional networks and heterogeneous graph transformers. This network analyzes the existing graph structure and trains itself to predict missing edges before they form in reality. It learns to forecast which vendors are likely to compete for an upcoming opportunity, or which incumbent contract is structurally vulnerable based on shifting semantic overlap. Once wired to production over a fully populated graph, this neural network transforms static historical storage into a forward-looking market signal engine. The system must go beyond the forecast itself and mathematically calibrate its own confidence in that prediction. Every claim passes through a 3-layer evidence architecture. Layer 1 extracts deterministic signals directly from the database, like historical recompete cycles and oversight citations. Layer 2 applies bounded large language model judgment, executing a likelihood ratio classification that requires a mandatory explainable rationale. Layer 3 executes mathematical convergence scoring. By applying Dempster-Shafer theory and Bayesian updates, the system combines multiple evidence sources without forcing a false sense of precision. The output is presented as a confidence interval rather than a definitive score. A narrow interval indicates a strong signal backed by strong evidence. A wide interval maps high uncertainty. Explicitly mapping what we don't know provides executives with a highly valuable decision signal on its own. This calibrated intelligence surfaces through dedicated API endpoints and MCP tools designed for GovTech platforms. Entering a procurement instrument identifier into the system generates a complete intelligence package, delivering agency fit scoring, contact mapping, and competitive positioning reports. The scale and complexity of the federal market mean that procurement decisions will continue to occur under conditions of incomplete context. State-of-the-art data science models this uncertainty, calibrating variance to provide a rigorous, evidence-based foundation for executive decision-making.